My dear students, in the previous video, I introduced the elementary transformations on matrices, that is elementary operations on matrices. That is, any two rows or columns of a matrices of a matrix are interchanged. That is, the first transformation is the elements of any two rows or columns are interchanged. Second one is the elements of any row or column is multiplied by the element, unknown corresponding elements are multiplied by an unknown non-zero number. Non-zero number. The elements of a row or column are multiplied by a non-zero number. And third operation is the elements of a row adding with the elements of any other row by multiplying a non-zero number. Similarly, the elements of a column added with the elements of another column multiplying by a non-zero number. Using these operations, we are going to introduce another topic, that is invertible matrices. Our next idea is invertible matrices. So in this video, I am going to introduce the idea invertible matrix. Invertible matrix. That is, if A is any square matrix of order M, definition. If A is any matrix, any square matrix, if A is any square matrix of order M and B is any other matrix and B is any other matrix of same order M. If A is any square matrix of order M and B is any other square matrix, it's also any other square matrix of same order M, then AB equal to BA equal to identity of order M. AB equal to BA equal to I. Then AB equal to BA equal to I. In this case, B is called I is the identity matrix of same order. I is also the identity matrix of same order M. Therefore, AB equal to BA equal to I. And in this case, B is called inverse. B is called inverse of the matrix A. Inverse of the matrix A and is denoted by A inverse. That is, B is called inverse of the matrix A and that is called B equal to A inverse. If A is any square matrix of order M and B is also any other square matrix of order same order M, then AB equal to B equal to I. If it is the case, if it is true, then B is called the inverse of matrix A and it is not to be A inverse, therefore B equal to A inverse. This implies from this, instead of A inverse, instead of B we can replace A inverse. Therefore A into A inverse equal to A inverse into A equal to I. Then if it is the case, in this case, A is invertible. In this case, we say that in this case, we say that A is invertible. That means we can find inverse of A. A is invertible means what? We can find the inverse of the matrix A. That means a matrix which is inverse or multiplying, you will get the identity matrix of the same order. The matrix and its inverse, or inverse and the matrix, multiplication of an inverse and the matrix gives you the identity. That is the definition. We will see this definition by our example. The concepts you have to understand thoroughly, then only the subject you can understand easily. The concept of every idea you should understand thoroughly. Then only the problem you can solve easily. Then only you can solve the problem easily. That is, with that, suppose if, example, if A is a matrix, 2, 3, 1, 2. This is a matrix A. And you consider the matrix B as 2, minus 3, minus 1, 2. This is your B. A is a square matrix of order 2 and B is any other square matrix of a same order 2. Then AB. What is AB? A into B. 2, 3, 1, 2. B is 2 minus 3 minus 1, 2. Multiplying first row, first column. First row, first column. And then first row, second column. First row, first column. 2 2s are 4. And 3 1 is minus 3. Similarly, first row, second column. 2 into 3 minus 6. 3 into 2 plus 6. And the second row, first column, 1 into 2, 2. 2 into minus 1, minus 2. Second row, second column, 1 into minus 3. And 2 into 2 plus 4. So simplification you get 4 minus 3, 1. Minus s plus x, 0. 2 minus 2, 0. 4 minus 3, 1. See, this is I. AB equal to I. Because this is I, nothing but I. Identity of order 2. AB equal to I. Similarly, what is BA? We will see. B. First you write B. By definition, I am checking the definition. B. 2 minus 3 minus 1, 2. B. A. 2, 3, 1, 2. Again, first row, first column. 2 2s are 4. And 3 into minus 1, minus 3. Second row, first row, second column. 2 3s are 6. 3 into 2, minus 6. Second row, first column. 2 into minus 2, minus 2. 2 into 1 plus 2. Second row, second column. 1 into minus 3, minus 3. 2 2s are 4. Again, this is equal to 4 minus 3, 1. 6 minus 6, 0. 2 minus plus 2, 0. 4 minus 3, 1. Which is also I. Therefore, we derived AB equal to BA equal to identity of the same order 2. Therefore, B is the inverse of the matrix A. Therefore, B is the inverse of A and is denoted by and B equal to A inverse. So, A inverse is what? 2 minus 3 minus 1, 2. This is what A inverse. Therefore, A is invertible. We can find inverse of A, therefore A is invertible. That is the example for inverse matrix. And the definition, we have derived the definition also by using this example. And next, some two theorems are there using the inverse of the matrices. The idea of inverse of the matrices are used in some theorems. First theorem, uniqueness of inverse. You will see one by one. And finding the inverse of given matrices or using the transformations we will see in the exercise. Now, the inverse of the matrices are determined using the transformation rules. At the first I explained in the video, and using this idea we are solving the problems. And before that, we are going to derive some two theorems on invertible matrices. Theorem 1. Uniqueness of inverse of a matrix. Uniqueness of the inverse of a matrix. That means inverse of a matrix is unique. Theorem says that the inverse of a matrix is unique. Inverse of a matrix is unique. That is the theorem. Proof: if A is any square matrix, suppose B and C are two inverses of matrix A of same order. Suppose B and C are two inverses of the matrix A, then we have to prove that B equal to A. If A is any square matrix, suppose B and C are two inverses of A, then we have to prove B equal to C, because two inverses are not different, they are one and the same. That means the uniqueness of matrix, uniqueness of the inverse is proved. So that is, B and C are two inverses of A, means it is nothing but they are equal. Now, I say, so first, if B is the inverse of A, case 1, if B is inverse of A, then B is inverse of A, AB equal to BA equal to identity. Suppose B is the inverse of A, by definition, AB equal to BA equal to I. Second one is, if C is the inverse of A, then AC equal to CA equal to I. AB equal to BA equal to I. If B is inverse, AB equal to BA equal to I. If C is inverse, AC equal to CA equal to I. Now we have to prove that B equal to C. For that, B equal to BI. So, because any identity matrix is multiplied by B itself. B into I is B. That is equal to B into I. I can replace I by CA. AC, correct. AC. I replace this I by AC because AC equal to I. From this, I associate BA into C. I associate BA. Matrix association multiplication is associative. Therefore, BA into C. What is BA? It is I again. IC. It's again equal to C. Therefore, B equal to C. You proved the theorem. Therefore, B equal to C. If B is, after applying this result, we will derive it as C. So, therefore, B equal to C. Hence, the theorem. Hence, the theorem. Okay. Then, one more theorem. Second theorem is that if A is the theorem says that A theorem 2. If A and B are two invertible matrices, if A and B are two invertible matrices of same order, then AB inverse, if A, the matrix A, if A and B are any two square matrices, invertible matrices, square invertible matrices, invertible matrices of same order. If A and B are any two square invertible matrices of same order, then you have to prove that then AB inverse equal to B inverse A inverse. That's what we have to prove. This is a theorem 2. AB the whole inverse equal to B inverse A inverse. Since AB is an invertible matrix, AB, the product AB into AB inverse equal to I. We know that AB is invertible because A and B are invertible, AB into its inverse, AB inverse equal to I by definition. Now, pre-multiplying by A, pre-multiplying by, see, AB inverse equal to B inverse A inverse, we have to prove this. For that proof, we know that since AB is invertible, AB into AB inverse is I. Now, pre-multiplying by A inverse on both sides, A inverse into AB inverse equal to A inverse into I. Pre-multiplying A inverse, pre-multiplying by A inverse. Pre-multiplying by A inverse on both sides. Okay. Now you associate this. This is A inverse into A into B into AB inverse equal to A inverse into I is A inverse. A inverse into I is A inverse because I is the identity matrix. Now you know that A inverse, since A is invertible, this is I. IB equal to AB inverse equal to A inverse. Because A into A inverse is I, because A is invertible. Now I into B is B. You know I into B is B. B into AB inverse equal to A inverse. Now again pre-multiplying by B inverse on both sides. That is B inverse into B into AB inverse equal to B inverse into A inverse. Now pre-multiplying by B inverse on both sides. Now this is B inverse into B is what? I. I into AB inverse equal to B inverse into A inverse. Over I into this any multiplication of I with any matrix is the matrix itself. Therefore, I into AB inverse is AB inverse. Therefore, last step. Therefore, AB inverse, I into AB inverse equal to right hand side B inverse into A inverse. Hence the theorem. Hence the theorem. Theorem is proved. That's all. The only step, last step I am writing here. So I into AB inverse is AB inverse equal to B inverse A inverse. That's all about the theorem. And we will solve some problems from the exercise in the next video. Thank you.